Welcome to Study Loop.
In this question, we are given the orbital period for Comet Hyakutake, and we are asked to find the semi-major axis of its orbit and then compare it to a couple of other distances. So the relationship we need between the orbital period of a body in an elliptical orbit is t equals 2 pi times a, the semi-major axis, to the 3/2 power divided by the square root of the gravitational constant g times the mass of the star that the body is orbiting. So we need to rearrange this to solve for our semi-major axis A. So we'll start by squaring both sides. And we're going to get A cubed equals G ms t squared over 4 pi squared. So clearly A was going to be equal to the cube root of G times the mass of the star, in this case the sun, times t squared divided by 4 pi squared. Swell. Now we need the period of the comet in seconds, and we'll end up finding A in terms of meters. So this period in seconds, we will take our 30,000 years and multiply by 365 days per year, multiplied by 86,400 seconds in 1 day. It's from a pop song from, I think, the late aughts. And we get 9.4608 times 10 to the 11th seconds. And I like to keep some extra decimal places when I'm doing my calculation and then round at the end. So now we're able to calculate that the semi-major axis for this comet's orbit, again, will be the cube root of g, which is 6.67 times 10 to the minus 11th, multiplied by the mass of the sun, which is 1.99 times 10 to the 30th kilograms, multiplied by this number of seconds squared, and then all of that divided by 4 pi squared. And I get a value of 1.4437 times 10 to the 14th meters per second. And then we are asked to compare to the average Sun-Pluto distance and the distance to Alpha Centauri, the nearest star to the Sun, which is 4.3 light years away. So first of all, our Sun-Pluto distance is, we'll just label it a distance, is 5.91 times 10 to the 12th meters. So just going off our powers of 10, we're, 2 magnitudes greater than that for this comet's semi-major axis. So we'll say approximately 1/100th of the semi-major axis. Or we could say that the semi-major axis is about 100 times this value. And then the Alpha Centauri distance we need to convert that 4.3 light years into meters. So we'll multiply by 3 times 10 to the 8th meters per second. And again, we'll do that same 365 days per year times 86,400 seconds, which you can get by taking 24 by 60 by 60. And I got that distance to be 4.068 times 10 to the 16th meters. Or in other words, that is about, looking at the powers of 10, it's about 100 times the semi-major axis. Or we could say that that semi-major axis is about 1/100th the distance. We have, 2 orders of magnitude difference, however you like to phrase it.